So you're me, and you're an MJT, and you're talking about something really interesting about free will, but you can't focus because you keep thinking about how, once the bell rings, you'll have 30 minutes to find Mr. Cher before the Shalom bus leaves. And you need to find him today because it's the deadline for out-of-town homecoming forms, and you're in one of those Ramah relationships, so you know. Anyway, just as a friend of yours begins to talk about hard determinism, you get to thinking, how can I find Mr. Cher as quickly as possible? You remember your physics teacher saying something about Heisenberg's uncertainty principle and how you can't determine both Mr. Cher's position and his momentum at the same time. So you decide that you're going to map Mr. Cher's position probabilistically, assigning a probability that he's at any point x in one-dimensional space at every time t. Once you've mapped out everything you know about Mr. Cher, you get to thinking, what if Mr. Cher is really just a quantum of an all-pervasive, homogeneous, administrative field? And since all fields are analogous, you generalize your example to all quanta, from administrative to electromagnetic. You remember your physics teacher referring to quanta as wavicles, and so you figure they behave like both waves and particles. You begin searching for a function psi to map your quantized wavicle. Well, it has to be wavy because it's waves, so that must mean trig, right? Okay, yes, but because you're a secret PhD in math, you find imaginary exponentials easier than trig. You'll get nostalgic about the pre-calc and the fun times with the e to the ix equals cosine of x plus I sine of x. But now you're freaking out because you just added imaginary terms to your function that represent nothing physical. You need to get rid of them, but how? Aha, multiply psi by its complex conjugate. Now you have the modulus of psi, your probability density, and the area under it will return the probability of finding your particle. You put on your math PhD hat again, and you solve the second-order differential equation that describes light waves for its most general solution, which you name Schrodinger's time-dependent solution to the wave equation. You're so creative with names. Anyway, you decide it'd be funny to find how quickly psi changes through space. You look at your result, and you're all like, hey, we talked about de Broglie relations in physics, so let's substitute things and find the wavicle's momentum. Then you erase all of the psi's and have a huge breakthrough. Physical constants in quantum mechanics aren't numbers, they're operators. So like, if you performed your momentum operator on psi, you'd get a function representing momentum. You use Newtonian mechanics to find a kinetic energy operator from the momentum operator. And then you have a temporary crisis because you've exhausted your spatial derivative. So now you decide to see how your function changes over your other variable, time, and then you use more de Broglie to find a total energy operator. You get excited because you realize that total energy equals kinetic energy plus potential energy. Well, whatever. You'll leave the potential energy operator to vary case by case, like whether you're launching Mr. Cher out of a catapult or dangling him off a cliff. You can write an abstract potential energy operator v of x and t and call it a day. Well, you don't call it a day, but you do call the thing on the right side a Hamiltonian, which is like a day. You're exhausted from all that math, so you begin to think about your administrative field macroscopically and how, at lunchtime, members of the administration will walk from initial position equals their offices with enough momentum to get to the cafeteria. If two of them collide, they'll talk and form an administrative wave of higher intensity. If they run into a wall, they'll turn around and keep going. Interference and reflection, just like light. But when you're dealing with the microscopic quantum of the field, like Mr. Cher, you only have a pretty good idea that he'll eat lunch in the cafeteria. But he could also be on a conference call on the third floor, or maybe even at CJDS for a visit. So the only way to be sure that you can find Mr. Cher is to put him in a box. Well, it's not exactly true. CJ's a box, and good luck finding him there. So you put him in a box of length L, whose walls require an infinite amount of energy to break through. You notice that the particle cannot leave the box because that would require infinite potential energy, so you're just dealing with x's in the box, so from 0 to L. Potential energy is 0 in the box, so you just get rid of v of x and t. Your constraints are also constant throughout time, so you decide that you're going to get rid of everything related to time in the Schrodinger equation. You solve your differential equation in its most general form and stick out some arbitrary complex numbers a and b as your coefficients, mainly for giggles, but also because that's how math works. But then you're all like, there's no probability of finding the particle on the edges of the box because that would mean infinity potential energy, so at x equals 0, your wave should be 0. Also, your sine wave should be 0 at the end of the box, so 2 pi times any integer n divided by k should be equal to L over 2, so k should be equal to n times pi times L. You're feeling pretty great about yourself because if you set the probability of the particle being inside the box to 1, you have your whole wave function, which you plug into Schrodinger's equation and solve for energy. Everything in this equation is a positive constant. The energy of your quantum is never 0. Also, the energy is not a continuous function. It comes in discrete packets that are n squared multiples of h squared divided by 2ml. You suppose it makes sense that kinetic energy is never 0 because if it were, the particle would be stationary, and you could determine its position and its momentum, and that would be way too easy. Also, Heisenberg said that that's impossible, and you're pretty sure he's smarter, or at least more knowledgeable than you are. And the whole discrete thing makes sense since these wavicles are quanta, and you can't have fractional quanta. So now all you have to do to find Mr. Scher is generate infinite potential fields around him. All you need is infinite power, which means infinite money. You don't happen to have infinite money, so what happens if you put Mr. Scher in a finite potential energy well? Well, you center the well about x equals 0, and the potential energy in the well will be 0, and the potential energy outside the well should be some constant. And your wave functions are no longer 0 outside the well, so there are going to be 3 different wave functions for each of the 3 regions. Perfect. You found your constraints. Now you work on the function inside the well and solve for your constants and map out a function. Now for the regions outside the well. Well, there could be 2 possibilities. Either kinetic energy is greater than potential energy and the particle is free, flying wherever it wants, or the particle is bounded because potential energy is greater than kinetic energy. Then you're like, it makes no sense to even talk about a free particle because that's not a very effective box then, huh? You do lots of cool mathy things and end up with equations in these forms. You remember hearing your teacher say that you want wave functions to converge, which just means you want the left equation to approach 0 at negative infinity and the right equation to approach 0 at positive infinity because the particle should have 0 probability of being infinity away, right? Also, the function should be continuous and smooth, so you do other things and perfectly map your function. You use Schrodinger's equation on psi to solve for energy and, again, find that energy comes in little discrete packets. Now that you have both cases modeled, you graph your wave function for the n equals 3 energy level and compare the differences between the infinite box and the finite well. You realize that the probability of finding Mr. Scher outside of your well is, it's non-zero. After all that, he might end up getting out of the box? What is the point of that? You call this stupid phenomenon quantum tunneling and resign yourself to life's harsh realities. You begin to wonder if Mr. Scher is ungrateful for all that work you did putting him in a lush, finite well. Will other, smaller things betray you like that? You start to think about the laptop in front of you. Your computer chip has a circuity thing in it, and that's probably got some transistors or something, which are super thin, like 1/2000th the thickness of your hair. There must be electrons flowing through this computer, right? But what happens if the parts in there get too small? Will the electrons start tunneling out? Then you realize that you're probably not the first person who realized that, and there's probably a 3 nanometer lower limit on the size of computer chips for that very reason. Just as you're getting ready to pat yourself on the back for discovering all that miraculously accurate info, you tune back into your determinist friend saying that everything in life is predetermined and that there is no such thing as free will. And you wonder if maybe she's right, because by Newton's laws of motion, if you know some initial properties of a particle like its location and its momentum, then you can predict its future location. You realize that if that's the case, then you could probably pull out your biobinder from freshman year and dig up some notes that'll let you predict the motion of chemical signals in your brain, and therefore your future actions. Future actions already determined? That doesn't sound like free will. But as you rack your brain trying to remember if you even took notes in bio, you realize that Heisenberg determined that you can't know a particle's position and momentum at the same time. So this is all indeterminate and probabilistic anyway, right? Right as you start to raise your hand, a thought hits you. What if no one is taking into account hidden variables? What if there are factors beyond our comprehension that cause probability functions to collapse into definitive facts, and because we can't fully understand them, the particles just seem to be behaving randomly? Just as your notions of free will begin to collapse around you, so do several superpositions of the wave function. The bell rings, and somewhere in the distance, a small cat dies.